Welcome back. I've got the pleasure to present our next speaker, with Sylvain from Swiss Re. His presentation titles "To Fly or Not to Fly, a New Bottom-Up Approach for Aviation Risk." Sylvain is a data scientist interested in modeling risks associated with complex systems. He might be able to tell us which airline we should or should not fly based on his newly developed aviation risk model. Sylvain, I'm sure everybody wants to know which airline performs best or worse. The stage is yours. Thank you very much.
Thank you for the introduction. And thank you everyone for tuning in for my talk. I'm a data scientist at Swiss Re, where I work on modeling a complex system in actually many fields of application, from wildfire monitoring using satellite images to healthcare forecasting. But in the last year or so, I've been working on aviation risk in particular, which I would like to talk about. First, for a word of caution, I take a data scientist point of view, a data scientist in insurance point of view. I'm obviously not a pilot, I'm not an aviation expert, so please take everything I say with a grain of salt. Huh? I think we've all, at least once in our life, asked ourselves the question of how safe it is to fly. You sit on the plane and you wonder, what are the chances I'm going down? And we've all look at the statistics, and thankfully they are pretty reassuring. Right? Chance of crashing in any flight is about 1 in 10 million, maybe 1 in 5, it depends how you count. Okay, so no risk, right? But we also all know that crashes do happen. And when they happen, there are tragedies with a lot of deaths, hundreds, 200 deaths. Remember last year there was an Ethiopian airline crash with the Boeing 737 MAX, or the Lion's Air with the same aircraft a year before. And many other losses happened in recent history. Of course, there are always human tragedy, but there are also financial losses associated with these crashes, millions and up to billions, actually, for very big crashes. And airlines cannot just pay out this amount. So what they do is that they buy insurance, the same way that you and me, we buy maybe a car insurance or maybe a house insurance to protect ourselves in case of a catastrophe. An airline is also buying an insurance. In case there is a crash, the insurance can pay for them. Now, if you change side and if you put yourself in the insurance shoes, right? Just saying that it's 1 in 10 million chance, pretty safe to fly, is not good enough to price an insurance. So what you need to do is actually have a pretty accurate vision of what are the chances. What is it exactly, this 1 in 10 million? And also, in case it happens, how bad can it get? What is the chance that it's 1 billion, 2 billion, or more? In this talk, I'm going to give you a bit of a high-level view of how we model this kind of risk, how we answer this question as an insurance. I will try to give you a peek under the hood of the model that we developed to do that, and conclude with a few general remarks. This is the old-school way to do aviation insurance, where you take a top-down approach. You look at the entire market, how often you have crashes, and then maybe you have intuition about which airline is more risky than another. You put that in the model, and in the end, you come up with a risk estimate. The new way of doing aviation insurance, which is what we try to do in this project, is to take the reverse approach, a bottom-up. So we look at all the individual flights that are planned by an airline, and then we model the chance of each of these flights to crash, and we model the distribution of the loss in case it crashes, and we put all that together to come up with an estimate of the risk of a given airline. Under the hood, what does it take to actually build such a model? It's actually not so easy. The first step, as in most data science projects, is to actually put the data together. Huh? And here the data that we have is a lot of information about all the flights that occur in the last 10 years. It's about 300 million, 400 million flights, so a pretty large amount. But you have to link these flights with accidents, historical accidents that we have access to, how much they cost, where they occur, etc. Information about airlines that are currently running, or the ones that are going bankrupt, and about the aircraft, what their age, what their type. Right? There are about 40,000 usually in the air. Right now it's a small fraction of that for reasons you're all aware of. But this was a lot of work to put all of it together, to then be able to construct a model. The model that we worked on is actually You can look at it in 3 different blocks. First part is just to model the chances of a crash. Then if you have a crash, you have to model the hull loss. What we call hull in insurance is the material damage to the aircraft, right? How much it costs if you do a scratch to your jumbo jet, right? How much it costs if you lose an engine. And then the final step is the liability, which is how much you have to pay for the death and injuries of the people that unfortunately got hurt if you have an accident. What we do is we take all these components, we put it together in a Monte Carlo simulation where we simulate what I call the worst year on Earth, where all the possible flights have crashed, and we look at what will have happened then, and then we combine that with a probability, and we estimate the risk of each airline in a normal year, right? Not the worst possible case. A few more details about each of these models, depending on the time I have. Frequency part, I think what's particularly interesting here from a modeling viewpoint is that you might think that 300 million flights is a lot of data, right? But then you have only 1,000 accidents. So if you look at it from a classification problem point of view, it's a very extremely imbalanced classification problem. So it's almost hopeless, right? So what we do to solve this problem that we aggregate, and we look at only at airline year level, and there it becomes a bit more manageable. You have a 10% imbalance, and then you can model that. And the technique we use more specifically is hierarchical Bayesian binomial regression, where hierarchical is to have some grouping effect for airlines, so to learn which airlines have had a bad history, which one didn't have accidents. The Bayesian part is to be able to put some prior and especially some regularization on the parameter, because it's still little data, so you need to constrain your solution. And the binomial regression is binomial because we have this grouping effect, so we have accounts, and then regression because we learned connection with characteristic of an airline, so age of the fleet and this kind of parameters. Here we can see some results. Just in a few words, what we're interested in is not to predict exactly the classify if you want, but is to know the probability are calibrated. So you want to show that when you say 1 in a million, it's really 1 in a million. When you say 2 in a million, it's really 2 in a million. And you can see in the plot that calibration is not so bad, not perfect. And if you look at the ROC curve, we can see that we do better than chance, right? But we're not all the way to the top. And I think the reason for that is that it's actually intrinsically a very hard problem. Right? If it was easy to predict which airline will crash on which flight, then we'll just not run this flight. Right? So there is a lot of stochasticity, and I think limit to predictability. The next part of the model is the hull, and for that, I think the gist of it, what's interesting, is that you want to model the distribution. So I want to know, in a given crash, what is the distribution of the hull loss, and we do that in 2 steps. First, we have to predict what is the hull value, because we actually don't know it. So we look at that age, model of aircraft, and so on, and we can predict the hull value. And then we model the hull loss as a fraction of this hull value. And to model this fraction as a function of covariates, we use a hurdle model with a beta regression. Hurdle is to put a chance to have a total loss, so 100% loss. You can see basically on the diagonal. And then the beta regression is to learn the distribution as a function of some covariates. Finally, the third part of the model is the liability. And here, what's interesting is also extremely rare event, because maybe we have 1,000 accidents, but actually very few of them go to very large losses in the billions and so on. So it's let's say, a very foolish exercise to try to fit a distribution on this part of the data. So what we have to do is to use expert information. And we use expert knowledge to know how many people are on board, what usually somebody costs if it dies, depending on nationality, etc. And we put all of it together. So I was curious to see how this brings back us to the original question of, okay, should I fly or not fly, right? And I picked an example. I looked from Zurich, what we fly out with different airlines, and just out of chance, fly from Zurich to Mallorca, 4 different airlines. And here you can see the chance of having an event in case you take a flight, in a million flights, right? And you can see for Swiss, for example, you have 0.5 in a million chance to have an accident. So it's not so small, but remember it's an accident, so it doesn't mean that you die. So if you look at chances that you have a total crash, then it starts to become actually very small, even smaller than the 1 in 10 million chance. I think from a user point of view, it doesn't matter like if it is 0.018 or 0.047, right? But from an insurance point of view, it makes a big difference because the price is probably double between both, right? So it does influence a lot. So that's exactly the kind of quantitative statement we wanted to be able to make. Now again, if you think about an insurance, it's just an illustration of not just the frequency, but the severity part. And if you imagine very imaginary, hypothetical product where you will insure an insurance for this specific line, and you say we insure everything that is more than 1 million, 100 million, or 1 billion, how much will you have to pay for this insurance? And here, without going into much detail, I think what it shows you is that using our complex model of all these different parts together leads to highly non-trivial loss distribution that shows we can have very specific price estimate for each of the airline depending on the risk. So, for example, if you take a 100 million threshold, right, you will have for Swiss airline you will pay this price, or for Chairline another price. But if you take another threshold here, that will lead to a very different answer because, for example, Chairline doesn't have big aircraft. So you cannot have 200 deaths if you have only an aircraft that has 50 seats, right? So simple question, it seems obvious, but you need a model that can actually recognize that and put that in the final figures. A few summary of and conclusion from that. First thing is, what did we gain by building such a complex bottom-up model by opposition to a standard top-down model? And I think that the first thing that we gain is interpretability. Because now, if we go to client and we tell them, look, we have to charge you so much for your insurance, we can actually explain why. We can say, look, it's because you have this and this aircraft, and you're flying this and this route, and these are more expensive than the other, hence we charge you more. So it's very transparent and very transparent and interpretable. Second main strength is that we can integrate expert knowledge with data-driven approach, which was a big plus, especially for the rare event and the tail of the distribution. And last but not least, I think from a stats point of view, you can look at it as a kind of generative model, not just a descriptive one, but a model, at least to some extent, allows you to answer a question of the what if type, right? What if now you change your fleet and you buy new aircraft? Or what if you open a new route in the US? How much will you have to pay more? Or what if, very actual, you have suddenly a pandemic, right? And then you have 95% of the flight that are not flying in different areas. The model will automatically reflect that in the price and tell you, okay, of course, I can give you the answer. Here you have to pay so much. Few takeaway to wrap up. So maybe I was not aware of that before, but airlines do buy insurance because when crashes occur, it's not only a human tragedy, but huge financial losses in the billion or multiple billion of cost. As an insurance, you have to build a model to do that. And what's interesting from a stats point of view is these are extremely rare events, and you need to develop a specific kind of method to deal with these rare events, integrating data-driven and expert knowledge together. Maybe from a stat point of view, what's also interesting is that you have to use, you're not interested just in a point estimate, but in distribution. And these are all techniques around distributional regression, which I encourage you to look into if you haven't used them in your day-to-day. But they are very powerful regression algorithms that don't only predict the expected value, but also the variance and the shape of a distribution as function of covariates. Finally, so what we did is that we didn't just answer, is it pretty safe to fly, but actually developed a fully bottom-up new model that can tell you very precisely how likely is it to have an accident, and interestingly allows you to answer what-if question, and is more robust to change in the distribution, such as we have, for example, with the corona pandemic. That's it. Thank you for your attention, and if you have any question or remarks, please shoot.
Thank you very much, Sylvain. That was quite interesting, and a number of questions were floating in. Okay. The first one is, you were talking about that this model is robust to changes. The question is actually, that came in, there are heaps of new innovations in the airline industry. Did you see changes in risk over time? Did they manifest themselves? Are any model drifts for the future expected?
Yes. It's a very good question. For the frequency part, at least, we notice there is more and more flights going on, but there are also less and less accidents. So thankfully, because the airlines improve in terms of security and technology, so definitely we see a drift of the frequency that goes down, everything else being equal, right? Of course.
Okay, and there's a very concrete question here for around slide 15. The Zurich-Mallorca numbers, are they real probabilities? Because somebody was amazed that there are bigger than one.
No, it's in 1 in a million flights,
It's
right?
1 in a million.
So basically,
okay.
you can think about it as an expected number of accidents in a million flights.
Clarified that.
No, you can be safe. You can fly. Otherwise, I would never fly.
Don't be afraid. And then, of course, there's the question ethics. I mean, how do you actually calculate the costs of death?
So we take a very pragmatic perspective, right? We're not normatively saying you should pay so much, right? We look at court decision and how much it happens in history that US court were paying for death, how much European court was paying, and then that's what we protect the insurance for.
Okay. Maybe one last question is Swiss Re looking into the reasons for the crashes, because the data used is frequency and costs actually generated.
Yes.
If it's going to be individual pricing for airlines, there might be an important factor in why the crashes appear. Is it lack of maintenance? Is it badly trained pilots? And could also, of course, help in the prevention area.
Yeah, it's always something I think in insurance you're excited about. You wish like you not only predict the risk but also prevent it. Unfortunately, I think our industry is a bit lagging in this respect. And if you think about it, I think it would be a bit presumptuous to say that us as an insurance, we understand better the risk than an airline, right? An airline, they are really hands-on. They have a sensor about every given flight, every one of their employees. So I think it would be a bit presumptuous to tell them we know better. So we look at it more from an outside perspective to try to understand which airlines are more risky than others.
Yeah. There could be an imperative to get this data from the airlines to be able to take it into account.
Yeah, if they are willing to give it to you, right?
Yeah.
Because they might be afraid they have to pay more insurance afterwards.
Exactly, yeah, that's right.
I think that could be interesting, definitely. Especially if we can reduce the risk together, right? And
absolutely. So, Sylvain, was very, very interesting. Thank you very much for your input and have a great day.
Thank you. Bye.